Thank you for the introduction. I'm Thodoris, and I'm going to present our recent work on enhancing the reliability of starting typing in compilers. The joint work with Stefanos and other collaborations from the Athens University of Economics and Business and Imperial College London. When Robin Miller, a famous computer scientist, provided his theory on polymorphic type, he wrote this famous quote that NP is the property of type safety in statically typed programming languages. This quote means that once you have a program that contains expression with valid types, then type errors are prevented from happening at runtime. Unfortunately, bugs in the compiler's typing procedures can invalidate this statement, and these bugs can introduce a lot of issues, including soundness issues, or cases where the compiler mistakenly rejects a well-typed program. Let's discuss some motivating examples. Here we have a tiny program written in Kotlin. In this program, we create a list of strings, and later we apply function map to obtain another list containing instances of class A. Recall that function map is a polymorphic function that takes two type parameters, expects a function that maps the type I to type O, and the final outcome of map is another list that contains values of type O. When the compiler typechecks this chain of calls, it needs to instantiate all these type variables. In situations like that, the compiler does so by solving a type constraint problem. However, due to a bug in the implementation, the compiler fails to substitute the type variable t with the concrete type string. And as a result, if we compile the program, we get this error message that says not enough information to infer type variable t. The problem in this example is that the compiler does not build the right type constraint problem because it misses some required constraints when encountering method references. So missing these required type constraints makes it impossible for the compiler to infer the right type for type variable t. Here is another bug, but this time this bug makes the compiler accept an ill-type program. Our program is written in Groovy, and we define here a polymorphic class that takes one type parameter whose upper bound is say. And the problem is in this assignment where we try to assign something of type A to a variable of type T. And unfortunately, A is not a subtype of T. And as a result, if we call this problematic function, the compiler accepts the program, produces the corresponding bytecode, and as a result, during the execution, we encounter a class cast exception that says class A cannot be cast to class B. Apparently, this type error should have been caught at compile time. So a question arises at the point, how can we detect such issues through automated means? Of course, we can employ compiler testing techniques. Compiler testing is a research area that has really thrived over the past decade, where we have witnessed techniques like C-Smith, equivalence, modulo inputs testing, and many other exciting methods. And these methods are highly effective in uncovering thousands of bugs in industrial strength compilers like GCC and LLVM. But unfortunately, these methods mainly focus on optimizing compilers. So what about testing type checkers? To answer this question, we leverage findings and observation of a previous bug study of typing-related bugs in JVM compilers. This study was published at Uppsala 21. And we leveraged the key findings of this work to design a framework that relies on both program generation and transformation-based compiler testing to reveal typing compiler bugs. Our framework consists of a program generator that yields well-typed programs that heavily rely on parametric polymorphism, while we avoid producing programs with complex control flow and arithmetic expressions, because we have found that these features are not relevant to revealing typing compiler bugs. The programs are written in an abstract language because we want to test diverse compilers. And on top of our program generator, we designed two mutations. The first mutation is called type erasure mutation, whose purpose is to reveal type inference bugs in the compilers. To do so, it removes type information from the program while preserving type program correctness. On the other hand, the type overwriting mutation The goal of type overriding mutation is to uncover soundness issue. To do so, it introduces subtle type errors in the program by replacing a type with another incompatible type. So what's the test oracle here? We expect the compiler to accept programs produced by our program generator and type erasure mutation because the resulting programs are well typed by construction. However, the test oracle changes in case of the type overriding mutation because now we expect the compiler to reject the outcome of this mutation. The result of our program generator and our mutations are then passed to language-specific translators, whose job is to translate an abstract program into a concrete source file, for example, a Java source file, which in turn is passed as input to the compiler under test, where, based on the given oracle, we compare the compiler output for bugs. Our abstract language supports various features that span from parametric polymorphism, standard language features like arrays, conditionals, and other object-oriented features like inheritance, dynamic polymorphism. But we leverage the findings of this bug study to prioritize features that are more likely to trigger typing compiler bugs. So that's why we pushed our efforts mainly on supporting parametric polymorphism, type inference, and many more. As we discussed previously, mutations, we have two mutations. Type erasure mutation reveals bugs in the type inference mechanism of compilers. To do so, it removes type information from an input program while preserving program correctness, and type overriding mutation. It introduces a subtle type error in the program by replacing a type with another incompatible type. To perform sound modifications, both mutations rely on some properties defined in an abstraction we call type graph. Type graph captures how type information flows between type parameters and declaration. A node in type graph is either a declaration or a type, and these nodes are connected with various edges with different semantics. To construct a type graph, we have designed intraprocedural type inference analysis. More details about the properties we define on type graph, you need to read our PLDI paper. But the key point here is that we use type graph to tackle some challenges when designing mutations. For example, in case of type erasure mutation, you can liberally remove type information from the program because you might end up in a situation where the compiler is no longer able to compile the mutated program due to missing type information. So at a high level, the algorithm behind type erasure mutation is that we first compute the set of nodes whose types are immutable, and then we select to remove the types from the maximal set of nodes. The word maximal here means that if we remove the type from one more node in the program becomes ill-typed. So in this particular example, type erasure mutation removes the type arguments from the two polymorphic constructor calls that take place during the body of M. And here's the mutated program, which is still well-typed. On the other hand, the type overriding mutation selects a node in the program at random and replaces its type with another incompatible type, meaning that the new type is neither supertype or subtype of the old type. So in this particular example, we replace the type argument of this polymorphic constructor call with type int, and this the mutated program is now contains type errors. Let's proceed with the empirical evaluation. We tested our techniques in a framework called Hephaestus. In Greek mythology, Hephaestus was the smithing god, and we used our framework to test the compilers of three popular languages, namely Java, Kotlin, and Groovy. Within 9 months of testing, we have found more than 130 confirmed and fixed bugs, out of which 86 bugs have been fixed by developers. Most of the discovered bugs are unexpected compile time errors, meaning that the compiler rejects mistakenly rejects a well-typed program. We have also found 22 soundness errors and 30 crashes. Regarding test case characteristics, 106 bugs are caused by program involving at least one feature related to parametric polymorphism. For example, declaration, parameterized classes, functions, etc. And interestingly, some developers commented in our reports that generics are the feature with the most latent concerns, and the generics bugs are tough, and so it was like in working on a difficult crossword or Sudoku puzzle every day. These findings validate our design decision to focus our efforts on parametric polymorphism and type inference, and they are consistent with the findings of our previous bug study that was published at Uppsala 21. Half of the discovered bugs were triggered by programs produced by our program generator, and the remaining half of bugs was triggered by our mutations. So as future work, I think we need to boost efforts on detecting soundness bugs. Our type of overwriting mutation is pretty simple. So what about devising a more sophisticated technique to detect such bugs? Because soundness bugs defeat the purpose of type safety offered by type systems in statically typed programming languages. We can also target other languages like Scala and TypeScript. We are currently working on a TypeScript implementation. And our program generator currently produces programs that contain roughly 500 to 1,000 lines of code. So we need to manually minimize them before opening bug reports. So what about devising a smarter program generator that produces small self-contained programs so that we don't need to employ a test case reducer? To conclude, as we saw, the implementation of compiler typing algorithms is challenging. So we leverage findings and observation of a previous bug study to devise techniques based on program generation and transformation-based compiler testing for detecting typing bugs in object-oriented, statically typed languages. Our implementation has found over 130 confirmed bugs in Groovy, Kotlin, and Java. Here's the pointer of our IFESTUS framework in case you want to try this out. Many thanks to developers, to compiler developers, in particular Groovy developers and Kotlin developers for addressing our bug reports. If you are interested in this work, consider attending our SIGBlank talk scheduled on this Friday. In this talk, we are going to provide details about our bug study that was published at Uppsala 21. So you can have an opportunity for finding more about them. And with that, I conclude my presentation. Thank you for your attention. I will be glad to answer.
Much of the previous work on finding bugs in compilers looked for bugs in optimization, which is a sort of continually changing area of compilers. I always thought of the type system as being fairly static. So once you find the bugs in the compilers, do you think that this is just going to be a solved problem? Or is it going to continue like the work has for finding bugs in the rest of the compiler?
That's a good question. I think that the implementation of type system is still complicated because language designers, language implementation need to keep up with the constant evolution of the languages. For example, 10 years ago, 20 years ago, C++ didn't support functional features, lambdas, closures, etc. All these new features, modern features, complicate the implementation of type systems. So I think that it's not going to be a solved problem.
Thanks very much for your talk. Are there any notable classes of programs that your generator can't generate, and hence areas where you're not going to find bugs using your tool?
Yeah, actually, we cannot generate programs that triggers features not supported by our abstract language. So, for example, imagine that you want to test Scala, then you need in order to find bugs related to Scala implicits, then you need to create abstractions of this feature in our abstract language.
So there's a trade-off between the complexity and the precision of type inference. Where do you get the ground truth for knowing whether the inferred types or whether types should be inferable for a given program? Is that in the language specification precisely?
Yeah, that's a good question. Actually, we have found a number of cases where the compilers marked our bug reports as not an issue or won't fix, and most of them were related to the implementation of type inference, because we encounter some decidability issues in type inference algorithms, and many developers classify them as a feature and not a bug.
Oh, yeah, thank you for the talk. I was wondering if you could speak about Groovy as being one of your benchmarks that you included. It seems like most of the bugs are found there, and I was thinking that Groovy was made to compete for languages like Python, right, that are interpreted. So I was wondering why you chose Groovy compiler as like one of the data sets.
Okay, thank you for your question. Actually, we chose Groovy because it's very close to Java. So once we have a support for Java, it was very easy to check our efforts, to check our tool on Groovy, because Groovy, at least in theory, should be compatible, syntax compatible with Java. And the reason why we found the most bugs in Groovy, because compared to the other language, Groovy developers fixed our bugs. It took them less time for them to fix the bug. So if you have a greater fix ratio, then you can uncover new bugs that are hidden by old bugs.
Towards the end, you said that you use a test case reducer and you would like to not use it anymore. Which one do you use, and why do you want to avoid using it?
Yeah. Actually, regarding these new program generators, we are going to leverage an insight from our bug study that showed that many typing-related bugs are triggered by programs containing or using the standard library of the language under test, such as collection API, sets, lists, etc. And these APIs heavily rely on parametric polymorphism. So you have already a wonderful collection of API methods that use parameterized types, upper bounds. So we can leverage these APIs, have a generator that use them in a complex manner so that we can find typing-related bugs.